It's one thing to build a perfectly engineered model race car in your garage.
Mm.
I mean, you control the environment, you control the temperature of the track, and when you hit the gas, the car performs exactly how you designed it.
Right, it's a completely closed system.
Exactly. But it is a completely different challenge to take that aerodynamic design and try to, like, manage an actual full-scale Formula One team racing in the middle of a hurricane.
Yeah, that is a massive shift in reality because in the garage, your only real concern is the math, right? The aerodynamics of the car's shape. Out in the hurricane, the aerodynamics almost take a back seat.
Right.
You're suddenly managing, global supply chains, pit crews operating under extreme stress, real-time telemetry from hundreds of sensors, and just constant, unpredictable weather that completely ruins your strategy.
Well, welcome to your final deep dive. For those of you following along, this is the grand finale, the concluding module of your graduate machine learning systems course.
It's been quite a journey.
It really has. And looking at the stack of materials we have for you today, your final lecture notes,
Yeah.
the architectural framework documentation, a few massive industry case studies, our mission here is to synthesize everything you've learned. Because taking your model from a Jupyter notebook on your laptop to a massive production environment, it fundamentally changes the problem.
It really does. It stops being a pure modeling or mathematics problem, and it becomes a distributed systems problem. That's the ultimate reality check of this entire course. A machine learning model only becomes a real system when it can scale across clusters, operate reliably, adapt to changing data, and, actually support responsible automated decisions.
Okay, so let's unpack this. Before we can even talk about deploying models to users,
Right.
we have to talk about how we train them when the data gets well, unbelievably massive.
Right.
Like, think about the global credit card network. You're analyzing spending behavior, merchant risk scores, device fingerprints for, what, 50 billion transactions a year?
Easily. You are looking at hundreds of terabytes of data.
Right. And if you try to run that on a standard laptop, or even like a crazy high-spec workstation, your machine will just instantly run out of memory.
Oh, absolutely. Or, best case scenario, it would literally take months to do a single mathematical pass over that data set.
Which introduces this really core concept of large-scale systems, which is data gravity.
Right, data gravity.
I think a lot of people just imagine data as this weightless, invisible thing floating in the cloud. But at the petabyte scale, data is incredibly heavy.
Very heavy.
It's like, imagine a massive mountain of iron ore. You don't load the entire mountain onto trucks and drive it across the country to a tiny forge. It takes too long, and the transport costs would just bankrupt you.
No, you build the smelting factory right on the mountain.
Exactly.
That is the perfect way to visualize it. Moving hundreds of terabytes of data across a network to your local machine is constrained by bandwidth limits, the massive computational cost of serializing all that data, and quite literally the speed of light. So you don't move the data to the computation. You move the computation to where the data lives. You scale out horizontally across a cluster of machines.
But the actual learning algorithm, like the gradient descent calculating the errors, that doesn't fundamentally change whether you have 1,000 rows or a billion.
Right.
Right? The math is the same.
Yeah, the mathematics remain identical. What's fascinating here is that at small scales, computation time, the actual number crunching, is your bottleneck.
Okay.
But at large scales, I/O just simply reading the data from the physical disk and moving it across the network, that entirely dominates the runtime.
Wow.
The whole challenge shifts to managing memory limits, minimizing disk reads, dealing with communication overhead between machines, and, handling fault tolerance when one of those machines inevitably catches on fire.
So at scale, choosing the right infrastructure framework matters just as much as choosing the right predictive model. So let's look at how those frameworks evolved, starting with MapReduce, which was revolutionary for its time, perfect for batch processing things like indexing the entire internet. But it turned out to be completely terrible for machine learning.
Right, and it's because of that disk I/O bottleneck we just mentioned. Machine learning is inherently iterative.
Yeah.
Algorithms require looping over the exact same dataset dozens or hundreds of times to slowly adjust their weights. MapReduce, by design, writes intermediate results back to the physical hard drive after every single step to ensure fault tolerance.
It's like, imagine reading a really dense textbook, but after every single sentence you read, you're forced to close the book, walk over to a filing cabinet, lock the book inside, walk back to your desk, sit down, and then immediately get up to retrieve the book for the next sentence.
Yeah, that would be agonizing.
Right. And if you do that for 100 epochs of a machine learning model, your system is spending 99% of its time opening and closing filing cabinets instead of actually learning.
Which brings us to the real breakthrough of Apache Spark. Spark solved this by introducing an in-memory, directed acyclic graph or DAG execution model.
The DAG.
Right. Instead of constantly writing intermediate steps to the hard drive, Spark caches the data in the cluster's RAM across multiple iterations. That single architectural choice makes iterative and interactive workloads vastly faster.
And the way Spark coordinates all this distributed RAM is pretty brilliant. You've got the Spark driver, which is like the central brain holding your main program.
Yes.
It talks to a cluster manager that negotiates the actual hardware resources.
Yeah.
And then you have the executors, which are the worker nodes out in the cluster that actually process your partitioned chunks of data in parallel.
The driver dictates the plan, but it uses this concept called lazy evaluation to optimize that plan before anyone does any heavy lifting.
Lazy evaluation, yeah.
You have transformations like filtering out bad data or, mapping a new column. And you have actions like counting the final rows. But Spark doesn't execute a transformation the second you write it in your code.
It just takes notes, it builds a logical blueprint. That DAG we mentioned, which is essentially just a one-way recipe of operations, Spark waits until you actually call an action to trigger the job.
And that laziness allows Spark's internal Catalyst optimizer to look ahead at your entire recipe and find shortcuts.
Oh, nice.
Yeah, if it sees that step 5 is going to filter out 90% of the data set, it'll just rewrite the execution plan under the hood to perform that filter in step 1.
Wow, so it skips the unnecessary work.
Exactly. It combines steps to figure out the absolute most efficient path to the final result, and you don't even have to write perfectly optimized code.
Wait, I do want to push back on something here, though. I see in the architecture notes this massive warning about the difference between narrow transformations and wide transformations, specifically warning against the dreaded shuffle.
Ah, yes, the shuffle.
If I have a modern cluster of, like, fiber optic linked supercomputers, shouldn't moving data around be the easy part? Why does everyone dread a network shuffle?
I mean, it seems like it should be fast, but a network shuffle is essentially a massive traffic jam.
Okay.
A narrow transformation, like a simple filter, happens independently. The executor just looks at its own isolated chunk of data in its own RAM and does the work. But a wide transformation, like if you're grouping data by a specific customer ID, that requires all records with that same ID to end up on the exact same physical machine.
Oh, I see. Since the data was originally scattered randomly across the cluster to be processed in parallel.
Suddenly, every single machine in your 100-node cluster is trying to send massive amounts of data to every other machine over the network simultaneously.
Wow.
The network switches just get totally congested. All that data has to be serialized into a format that can travel over the wire and then deserialized on the other end.
Sounds expensive.
It is. And because RAM fills up during this massive exchange, the excess data often has to spill over onto the slow physical disks anyway. So network shuffles are really the main performance killer in distributed ML.
Which is why modern Spark pushes developers toward DataFrames and MLlib pipelines. Because by organizing data into strictly typed columns rather than loose objects, that Catalyst optimizer can slash through inefficiencies and minimize those expensive shuffles.
Exactly. It gives you a highly scalable, reproducible workflow. And if we connect this to the bigger picture, once you have a scalable engine like Spark, you've essentially conquered the compute bottleneck. You can process petabytes of data, but then you hit a new ceiling. Traditional structured models simply cannot capture the complexity of massive, unstructured data sets.
Right, because a classic linear regression isn't going to process a million raw image pixels or raw audio waveforms. This forces a transition into the broader AI ecosystem and the real heavy hitters, which are deep neural networks.
Yes, we shift from old-school rule-based AI to modern data-driven learning. And the absolute key concept here is representation learning.
Let's break that down.
Sure. In traditional machine learning, a human domain expert has to manually engineer the features. For fraud detection, a human literally has to code a rule that says, look at the ratio of transactions between midnight and 3 a.m.
Okay.
But with high-dimensional data, manual rules break down. You can't write a manual rule for the pixel arrangement of a fraudulent document. Neural networks enable representation learning, meaning the network learns those internal task-specific features directly from the raw data itself.
Let's walk through the anatomy of how that actually works for a second. You start with artificial neurons, organized into multiple hidden layers to form multi-layer perceptrons.
Right.
But if you just stack neurons, it's really just a giant linear math equation. So you apply activation functions, which is really just a fancy way of saying you introduce nonlinearity, allowing the network to learn complex, squiggly boundaries instead of just drawing straight lines.
Sure. And then at the very end of the network, you use a loss function, which encodes your modeling assumptions and basically calculates a single number representing exactly how wrong the network's predictions were compared to the actual truth.
And here's where it gets really interesting. Because once you know how wrong the network is, you have to correct it. We have to talk about backpropagation.
Ah, backpropagation.
The name alone just sounds like sci-fi AI magic, right?
Right.
Like the machine is somehow thinking backward in time.
It seems incredibly mysterious, I know, but we have to demystify it right now. Backpropagation is not magic. It is simply structured calculus.
Okay.
Imagine a factory assembly line building a car. At the end of the line, the inspector realizes the car is missing a steering wheel. Backpropagation is basically the process of the inspector walking backward down the line, telling the final station they contributed 50% to the error, the middle station 30%, and the first station 20%.
It's just assigning blame layer by layer.
Exactly. Mathematically, it is a direct application of the chain rule from calculus distributed over computational graphs. Modern systems use automatic differentiation. So as the data moves forward through the network, the graph records every single mathematical operation.
Right.
Then it automatically computes the derivative path backward, calculating the exact gradient, the specific direction and magnitude, that we need to adjust millions of weights simultaneously using highly optimized matrix algebra.
But, and this is a massive reality check for you listening, just because you can use a neural network doesn't mean you always should. I mean, they are powerful, but they are highly conditional tools.
This raises such an important point. When do neural networks fail you? I mean, they're unparalleled for high-dimensional data like text and images, and for finding incredibly complex feature interactions.
Right.
But they will frequently underperform a much simpler model, like a random forest, if your data is scarce, or if you're working with highly structured tabular data.
Or if your deployment context requires strict interpretability. Think about predicting hospital readmissions. If a doctor demands to know why a patient was flagged as high risk, you cannot just point to a matrix of 2 million hidden, uninterpretable weights.
No, they won't accept that.
You need an explainable model. Neural networks are tools, not universal silver bullets.
Their success depends entirely on the scale of your data, the structure of your features, incredibly careful validation, monitoring, and the real-world deployment constraints, plus all the responsible AI considerations.
Okay, so let's say you navigate all of that. You find the perfect use case. You design a massive deep neural network, train it on a 100-node Spark cluster, and successfully deploy it into your user-facing app. Your metrics look phenomenal.
Are you done? Definitely not.
Can you just wash your hands and move on to the next project?
Absolutely not. In fact, your job has basically just begun.
Because the real world doesn't stand still. Models degrade the second they hit production. Which brings us to an entirely new discipline, MLOps.
Right. MLOps takes the core principles of software DevOps, continuous integration, automated testing, and extends them to machine learning. But it is fundamentally more complex.
How so?
Well, in traditional software engineering, the only thing that changes in production is your code. If the code is well tested and bug-free, the application just continues to work indefinitely.
But wait, let's follow that logic.
Mm.
If my machine learning code is perfectly written, and I don't introduce any new bugs, why would the model's accuracy suddenly plummet in production?
Because in machine learning, it's not just the code that dictates behavior. The data dictates behavior, and data is a reflection of the real world.
Oh, right.
You inevitably face data drift, where the distribution of the incoming input changes. Maybe a physical temperature sensor starts to degrade and sends slightly higher baseline readings, or a brand new demographic starts using your app, generating feature distributions the model has literally never seen before.
Or even worse, concept drift. That is when the actual fundamental relationship between the input and the target variable changes completely. Think about a perfectly calibrated fraud detection model built in, say, 2019. By April 2020, that model would be flagging every single person as a fraudster because the pandemic caused consumer spending habits to radically change overnight. What used to look like an anomaly was suddenly perfectly normal.
Right. Add in schema changes upstream, feature leakage, changing user behavior, and operational latency constraints. A machine learning model is really a living, breathing system that is constantly decaying.
So to keep it alive, production ML requires a totally different set of tools. You need strict reproducibility, versioning for both your code and your massive data sets, continuous training pipelines, model registries, automated validation gates, and the ability to instantly roll back to yesterday's model when today's model just goes completely off the rails.
A really critical architectural strategy to handle this continuous evaluation is the predictor monitor pattern.
Well, let's break down the mechanics of that pattern.
Sure, so you isolate the system into two distinct components. The predictor is a highly available, low-latency microservice. Its singular job is just to receive a user request, apply the model weights, and return a prediction in milliseconds. It's the front line.
But you don't want to bog down that lightning-fast predictor with heavy statistical analysis, trying to figure out if the model is drifting.
Exactly.
Yeah.
So you introduce the monitor. This is a separate asynchronous service. It just quietly ingests the logs and prediction metrics from the predictor in the background. It compares today's live distribution against the historical training distribution, computes drift scores, and triggers automated retraining alerts.
Nice.
And it does all of that without ever stealing compute cycles or slowing down the live user experience.
Separation of concerns. I love that. But to actually implement these complex MLOps patterns reliably, you aren't just writing dash scripts on a server in a closet. We have to look at production-grade workflows and cloud platforms. Scale requires robust infrastructure.
Right. If we look at Google Cloud Platform as our blueprint, keeping in mind that AWS SageMaker and Azure Machine Learning utilize very similar architectural patterns, you see an integrated ecosystem designed explicitly for this lifecycle.
Yeah, on GCP, you have Vertex AI acting as the central nervous system for training jobs and model endpoints. You leverage Cloud Build to orchestrate your CI/CD pipelines. BigQuery handles the massive structured data warehousing, Dataflow manages the real-time streaming ingestion, and cloud storage acts as your artifact repository.
While those managed serverless tools are incredibly powerful and fast to deploy, many organizations actually opt for Kubernetes and Kubeflow instead.
Why take on the headache of Kubernetes if the managed cloud services do all that heavy lifting for you?
Vendor neutrality and portability. Kubernetes gives you a universally standardized stack. You aren't permanently locked into Google's pricing or AWS or Azure. You can lift and shift your entire ML infrastructure to any cloud or even run it on premises.
Okay, that makes sense.
However, that portability comes with a massive trade-off. It shifts the operational burden entirely onto your team. You are now responsible for cluster upgrades, security patching, and deep reliability engineering.
You essentially own the hurricane at that point.
Exactly.
But regardless of whether you choose managed services or Kubernetes, there is a foundational layer beneath all of it that dictates your ultimate success or failure, right? DataOps.
DataOps is the bedrock. You need reliable data ingestion pipelines, strict schema enforcement, automated data quality checks, feature consistency, and pipeline observability. Because if your DataOps foundation is fragile, you simply cannot trust the data flowing into the model. And if you cannot trust the data, the most mathematically advanced, perfectly optimized neural network in the world is completely useless.
Garbage in, garbage out, just operating at petabyte scale. So how do we evaluate if an organization is actually doing this correctly? We measure them against MLOps maturity levels. Think about your current company or the lab you work in right now as we walk through these. Level 0 is entirely manual experimentation.
At level 0, data scientists train a model locally, maybe save the weights, and literally hand off a Jupyter notebook to an engineering team to figure out how to recode it for production.
Wow.
Yeah, it is slow, highly prone to human error, and creates a massive risk of training serving skew, where the way features are calculated in training is subtly different from how they're calculated live.
Then you graduate to level 1.
Level 1 introduces automated continuous training, or CT, pipelines.
Yeah.
You aren't manually running the notebook anymore. The model retraining process is orchestrated. It automatically kicks off on a nightly schedule or, when the monitoring service detects new data drift.
But the holy grail of this entire field is level 2. Full CI/CD-driven model promotion. At level 2, production ML is treated as a fully managed automated system.
Right.
Code changes, feature engineering updates, and new data all pass through automated validation gates. The system tests the pipeline code itself, validates the statistical accuracy of the new model artifacts, and autonomously moves the best model through staging, testing, and finally into controlled release environments.
That is the critical distinction. At level 2, you aren't just automating the model training, you have automated the infrastructure and the pipelines that actually produce the model. and monitoring signals can trigger retraining, rollback, or a complete redesign.
Okay, we have covered an immense amount of ground today, from the absolute limits of a single laptop hitting the wall of compute all the way to level 2 cloud deployments orchestrating neural networks. Let's synthesize the journey. I want us to distill this entire course down to the absolute essentials.
Sure, let's do it. If we look back at the whole journey, the first major realization is that machine learning at scale is a systems problem, not just a modeling problem.
Which means dealing with data gravity, managing disk I/O, minimizing network shuffles, skew, memory limits, and designing for fault tolerance. That's takeaway 2.
And that necessity drove the evolution of our frameworks. Takeaway 3 is that Spark supports scalable iterative ML through in-memory, DG-based execution, and MLlib pipelines.
Then we explored the modeling side. Number 4, neural networks enable representation learning, bypassing manual feature engineering, but they require sufficient data, careful optimization, and strict monitoring.
We also demystify the engine behind those networks for number 5. Backpropagation is not magic, it's structured calculus over computational graphs.
And building a model is only day 1. Number 6, MLOps makes ML reproducible, deployable, monitorable, and maintainable in the face of continuous real-world drift.
Which culminates in the final takeaway, number 7. True CI/CD for machine learning requires validating far more than just software code. You must automatically validate data, features, and performance before ever promoting a model to production.
So what does this all mean? We started this deep dive by comparing a model race car in a quiet garage to managing a Formula One team in a hurricane. But think about the trajectory of level 2 maturity. If you build an MLO system that detects its own drift, updates its own features, orchestrates its own continuous retraining, and promotes itself through CI/CD validation gates to production, at what point does the human stop being the machine learning engineer and simply become the observer of an autonomous intelligence factory?
That is a profound paradigm shift. As your systems mature, your role fundamentally elevates. You transition from building the machine to building the machine that builds the machine.
Definitely something to ponder as you look at your own pipelines. Congratulations on completing your machine learning systems course. You've conquered the math, you've mastered the infrastructure, and now you know how to build systems that survive the hurricane. Thanks for joining us on this final deep dive.